Okay, 2.4b, reflections of functions. So we have to talk about what is a reflection. So reflection is a transformation in which a figure is reflected over a reflection line. Okay, the two reflections that we're going to really talk about is the reflection over the x-axis and the reflection over the y-axis. Okay, so as an example, if we had this root function and we wanted to reflect it over the x-axis, it would reflect to this dotted line or the dotted curve. Okay, in this case, what happens is with a better arrow, the coefficient or like the number in front of f at x is going to be negative. Okay, so if it's in this position here, we know that it's a reflection over the x-axis. Okay. Now, again, the same thing for like the second box here. We have the root function, and if we want to reflect it over the y-axis, it's going to reflect this way. Okay, in this case, because it affects the x's, like say 3 is now going to be mapped onto -3. 4 is now going to be mapped onto -4, right? Because it affects the x values, it actually is going to be right beside the x. So f at -x. And this is a reflection in the y-axis. Now, if you want to take a look at the double reflection, again, let's start with the root curve. We would have reflected it in the x-axis, and then we could reflect it in the y-axis as well. Okay, so that double reflection would be, this is a reflection in the x-axis, and this is a reflection in the y-axis. Okay, so the positioning of those negative signs really matters. Okay, so when we take a look at actual mapping notation for reflections, if it's in front of the function, then it affects the y-coordinate, right, like the up and down. And what we do is we take the negative of every single y-coordinate in, like, say, the table of values. Okay, and if the negative sign is grouped in with the x, then it affects the x-coordinate. And then what we do is in the table of values, we negate, or like we flip the sign of every x value. So in general, the mapping notation xy would get mapped onto -x, -y. Okay, this negative here affects f at x. Remember, f at x is actually another way of saying like y, but just in function notation. And we multiply all the y's by -1. And this negative sign here affects the x. We multiply all the x's by -1. Okay, example 1. Given the function f at x, write an equation to represent each of the following, and then state the mapping notation. Then what we're going to do is sketch the graph and then state the domain and range. Okay, so if we have a function and it's f at x equals x squared, so obviously this is the parabola. If it's reflected in the x-axis, what that's going to look like as a function is -x squared. So what's going to happen is, because it's reflected in the x-axis and this is getting reflected down, it's actually going to affect these y values. So every time we see y value, we are going to negate it, okay? Or in other words, the f at x value. So all of these x's are going to stay the same, -2, -1, 0, 1, 2. But from the original graph, we're going to take all these y values and we are going to flip the sign. So -4, -1, 0 doesn't have a sign, so it's just 0, -1, -4. Now if we were to go over here and graph this, it's going to look like this. I have f at x, function notation. Okay, so for this one, domain's actually not changing, okay, XER. However, the range is going to change. So instead of like opening up, it's going to open down. So y is going to be less than or equal to 0. Okay, and I just want to highlight that this is going to be, if this is your vertex from the original, this is also going to be your vertex after the transformations. Okay, now if we have f at x and it's reflected in the y-axis, that means that it's going to reflect like this. We can denote this by putting bracket negative x bracket squared, because we want to group that negative right in with the x. So what's going to happen is every single x term we are going to negate. So negative 2 goes to 2, negative 1 goes to 1, 0 stays as 0, 1 goes to negative 1, 2 goes to negative 2. Okay, the f at x's, there's no transformation on the y's, so we just leave them as is. Okay, so if we were to actually graph this, it's actually going to be the same graph here, because parabolas have the characteristic that they're symmetric about the y-axis, so we have the same graph. So like our new domain is going to be XER, which is the same, and our new range is going to be YER such that y is greater than or equal to 0, right? It's like that point here, because we go up, and that's the same as well. Okay, now we're going to take f at x equals x squared, and we're going to reflect it in both the x and the y-axis. In this case, the equation would be negative f, I'm going to actually put x squared, negative of bracketed negative x squared. This is the reflection in the x-axis, this is the reflection in the y-axis. So we're going to negate the x's and we're going to negate the y's all the way down. I'll set up my brackets. Okay, so this is going to turn into 2, negative 4, 1, negative 1, 0, 0 stays the same, negative 1, negative 1, negative 2, negative 4. Okay, so if this is our graph, which is f at x equals negative x squared, we are going to have a domain of the same, XER, right? Because the x's go left and right forever. However, the y value is going to be less than or equal to 0. So what happened here is first we flipped it, say, this way. It doesn't even matter. And it yields the exact same parabola. And then we flipped it across the x-axis. And then it just yields the reflection. Okay, example 2, we're going to cover the root x function. Okay, so the root x function looks like this. If it's reflected over the x-axis, remember we want to just put the negative sign out front and then put the function. Okay, so this is going to affect the y values, so we're going to negate all of the y's. So these x's stay the same, 0, 1, 4, 9. And these y's all negate. So 0 stays the same, 1 goes to negative 1, 2 goes to negative 2, 3 goes to negative 3. And when we graph this, 4, negative 2, and then 9, negative 3. When we graph this, so f at x equals negative root x, it's going to look like this. Okay, so I'm going to set up the domain and range. The domain is still from 0 and bigger, so x is greater than or equal to 0. The y is different though, so the y still starts at 0, right? Like this essentially, if you think about it, this is going to be like, you know, your fake vertex, your starting point. So instead of opening up, it's now actually going to open down. So y is less than or equal to 0. So this one right here, of course, the range is going to change because we're affecting the y. Okay, now if we are reflected in the y-axis, and to reread that, okay, we are going to get root of bracketed negative x. So what that's going to do is every single time we see an x, we're going to negate it, and the y's stay the same. So these y's stay the same. I always do the one that stays the same first, just to set up my question. Okay, and all the x's are going to negate. So 0, -1, -4, -9. 4, 2, 9, 3. So this is the reflection in the y-axis. Okay, so the domain is going to change because obviously we reflected the x's. The y is going to stay the same because nothing happened to the y. So from the original, y is greater than or equal to 0, right? Because it starts at 0 when it goes up. But the domain, that's the one that's going to change. So the domain starts at 0, right? So our starting number is still right here, but it's going to go less than. So x is less than or equal to 0. Okay, so now let's do the double reflection. Reflection in the x-axis and the y-axis. So we're going to have a negative in front of our function, but we're also going to have a negative under the root sign. So we're going to have negative x, negative y. Every single number here is going to be negated. So 0, 0 stays the same because 0 doesn't have any like positive or negative sign on it. 1, 1 is going to switch to -1, -1. We have -4, -2. Then we'll have -9, -3. Okay, so then here is our function. So essentially what we did is we reflected this over the x-axis and then reflected this over the y-axis. Okay. Because we have a transformation on both the domain and range, both the domain and range, or both the x and the y, both the domain and range are going to change. Okay, so we're still going to start at this point 0, 0. Okay, so that's still going to be our reference point. So here's our reference point. The x's go this way, so they get smaller. X is less than or equal to 0. The y's go this way, so they're smaller. Y is less than or equal to 0. Okay, so for f of x equals 1 over x, when this is reflected in the x-axis, again, we put the negative sign in front of the function, and then we can write 1 over x. Okay, so in this case, the x's are going to stay the same, the y's are going to change. The y's are going to go to negative. Okay, so this is a reflection of the x-axis. It's going to affect these numbers right here. So the -1 and 1 stays the same. And then the y's negate. So we have 1 and -1. Okay, this is the function 1 over x. And just to review, when we use points, we actually only have to use 2 points. We have to use this point here and this point here. The reason why we only have to choose 2 points is because we really focus on where the horizontal and vertical asymptotes are here. Okay, so this is going to be the vertical or the horizontal asymptote y equals 0 and the vertical asymptote x equals 0. Okay, as long as we know, I call it quadrant, as long as we know like what quadrants these 2 points are in, and they're always going to be kitty corners, so like they're always going to be opposite of one another. They're never going to be adjacent or like beside one another. Okay, so as long as we know where those 2 points go, it's going to roughly look like this, like a curve that approaches both asymptotes. Okay, so unless there are shifts, then the horizontal asymptote is going to stay as it is, and the vertical asymptote is going to stay as it is. So our new function looks like this. So all we have is 2 points, And then we're okay with that. And that's our new function. So this is f at x equals negative 1 over x. Oh, domain and range. So domain and range for this one actually doesn't change, okay? And that's because the domain and range are both based on where the x and the, or sorry, where the horizontal and vertical asymptotes lie. So x does not equal 0 and y does not equal 0. Those asymptotes haven't moved. So unless there's a translation where you're shifting up, down, left, or right, the domain and range are going to stay the same. Okay, now if this is reflected in the y-axis, so the y-axis is here, meaning this curve is going to reflect here, this part of the curve is going to reflect here. Remember, this is one graph. Even though it's discontinuous, you have to pick up your pencil, you have to draw two separate curves, it's still representing 1 over x. So we can write it as 1 over like negative x. If you actually think about it though, this negative sign, in order to simplify, would come up, and then 1 over negative x is actually going to be equivalent to negative 1 over x, right? Which is, so this is a reflection in the y-axis is actually equivalent to the reflection in the x-axis mathematically, like algebraically. Then graphically, we're going to flip every x and keep the y. So these two are going to flip, and then negative 1 and then 1. There's no shifts, so the horizontal and vertical asymptotes stay. So if you actually do this graphically, we see that these are equivalent as well. So reflecting the original in the x-axis is equivalent as reflecting it in the y-axis. And because there are no shifts, domain and range stay as x does not equal 0 and y does not equal 0. Okay, now let's do the double reflection where we reflect it in the x and the y-axis. So first we're going to reflect it down and then we're going to reflect it over. Okay, so we could write this as negative 1 over negative x. But if you actually think about it mathematically, in order to simplify this, we would bring this negative sign up. So then we'd have negative of negative 1 over x. In order to simplify this, it would just be positive, or just normal, 1 over x. So mathematically, it's going to actually be the same, equivalent to the original. And when we go ahead and negate both, like negative 1, 1 is going to plot on 1, 1, which is here again. And 1, 1 will plot on negative 1, which is here, giving us this graph. So negative of 1 over negative x. Okay, the horizontal and vertical asymptotes stay the same. That means that our domain and range also stay the same. X does not equal 0 and y does not equal 0. Okay, example 4, given the function f at x, write an equation to represent each of the following transformations. Okay, so this is the combination of 3 different lines. So this doesn't take on an actual like formal equation. So what we're gonna just generally say is this is the function f at x. Okay. And then when we actually state the equation, f at x is going to become, like, reflecting the x-axis is going to be negative f at x. So that's like the general form in which we can write this. Then we're going to state 4 points on the graph and then transform them. So we know that the mapping notation, we are going to flip every single y value. So we can either write it as negative f at x or negative y, okay? I should be writing it as f at x since we're using function notation. Okay, so what I'm going to do is I'm going to just choose 4 points on the graph. I would always choose turnaround points, and I'm going to write them right here. Okay, so we have -9, 6, -5, 6, 2, -2, and then 8, 0. Okay, all of the x's are going to stay the same, so -9, -5, 2, and 8. Now, every single y value is going to flip. So 6 and 6 go to -6, -6, -2 goes to 2, 0 stays. So when we graph this, we're going to graph 1, 2, 3, 4. That is going to be our function, -f at x. Okay, very general function there. Now, domain and range. We're going to start, this is continuous, so we're going to start with x is an element of the real number system and y is an element of the real number system. And we know that our x goes from -9 all the way to 8. So -9, x, 8. Okay. And then we know our y value goes from -6 all the way up to 2. Okay, we're going to do the exact same thing for b, except for this time we're going to reflect it in the y-axis. So I'm actually going to copy this table of values here, -9, 6, -5, 6, 2, -2, 8, 0. Okay. Now, if we reflected this f at x in the y-axis, it's going to reflect this way. So it's going to affect the x's. Our equation in general is going to be the function at -x. So we're going to negate all the x's and we're going to leave the y's. So we have 9, 5, -2, -8. Okay, and then we're going to leave the y's. 6, 6, -2, 0. 6, 6, -2, 0. So when we go ahead and graph this, we're going to graph -9, 9, 6, 5, 6. I always connect them right away because sometimes when you have a bunch of points, you connect them in the wrong order. -2, -2, and then -8, 0. Okay, so this here is the reflection in the y-axis. Now I'm going to set up our domain and range, XER, YER. And we know for this one, x is going to be between two numbers, and y is also going to be between two numbers. Okay, so x is going to be between -8 and 9. Y is going to be between -2 and 6. Okay, this time we're going to do the double reflection. Okay, so we're going to put one negative sign out front of the f at x and one inside the bracket with the x. Okay, we're going to reflect the x and we're going to reflect the y. So this is our mapping notation. And I'm going to write the -9, 6, -5, 6, 2, -2, and 8, 0. Okay, so if we were to double reflect this function f at x, we're going to get 9, -6, 5, -6, -2, 2. Oh, I'm 2, -2, 2, and then -8, 0. Let's see if this turns out. 9, -6, 5, -6, -2, 2, and -8, 0. And this is negative f at negative x. Okay, let's set up the domain and range where x is going to be between two numbers and y is also going to be between two numbers. So x is going to be between negative 8 and 9, and y is going to be between negative 6 and 2.